Find a dark enough sky, away from city lights, and look toward the constellation Orion on a clear winter night. Just below the 3 stars of Orion's belt, faintly visible to the naked eye as a smudged point of light that refuses to resolve into a sharp star no matter how long you look, is the Orion Nebula. It has been there every winter night for the entire history of human existence. Every civilization that looked up at that part of the sky saw it. Most assumed it was simply a blurry star, an imperfection in the celestial sphere, something the eye could not quite bring into focus. What it actually is bears no resemblance to that assumption. The Orion Nebula is a cloud of gas and dust, roughly 24 light-years across, sitting about 1,344 light-years from Earth. The light arriving in your eye when you look at it left that cloud before the Norman conquest of England, before the Viking Age, before the fall of Rome. The smudge you see is not a point. It is a structure larger than any distance the human mind evolved to comprehend, glowing because the young stars forming inside it are pouring ultraviolet radiation into the surrounding gas, stripping electrons from hydrogen atoms, and the electrons releasing that energy as light when they recombine. The colors in deep telescope images, the pinks and reds and blues, are not artistic choices. They are the specific wavelengths emitted by specific atoms responding to specific energies. The nebula is writing its own composition in light, and it is doing something else. Inside that glowing cloud, at this moment, stars are being born. Gravity is pulling gas together into dense knots that will eventually ignite. Some of those knots are already proto-stars, collapsing objects that have not yet crossed the threshold into nuclear fusion. Some will become stars like the Sun. Some will be surrounded by disks of leftover material that will over millions of years aggregate into planets. The smudge below Orion's belt is not a passive decoration on the night sky. It is a factory running continuously, producing the same kinds of objects that produced every atom currently inside you. So what is a nebula, stated precisely? A region of interstellar gas and dust dense enough to be detectable either through the light it emits, the light it reflects, or the light it blocks from sources behind it. That definition is almost insultingly plain, given what nebulae actually are and what they actually do. Where did that material come from? Why does it behave the way it does, rather than simply drifting inertly through space forever? And what does any of it have to do with the existence of everything around you right now? If you like exploring questions like these, feel free to leave a like and subscribe. And if there's something about the universe you find yourself wondering about now and then, drop it in the comments. It might become the next question we dig into. For now, let's get back to that question. The material in a nebula is not random. It has a history. And that history begins further back than any star, further back than any galaxy, all the way to the first moments after the universe itself began. 13.8 billion years ago, the universe was not a place that contained anything recognizable. No stars, no galaxies, no planets, no chemistry. Just an extraordinarily hot, extraordinarily dense soup of energy and elementary particles expanding outward in every direction simultaneously. In the first few minutes of that expansion, as temperatures dropped to levels where protons and neutrons could stick together without immediately being torn apart again, the universe produced its first atomic nuclei: hydrogen, helium, trace amounts of lithium, nothing heavier. The physics of those first minutes did not allow for anything more complex, and the expansion was already carrying matter apart faster than the reactions needed to build heavier elements could proceed. What the universe contained after those first few minutes was roughly 3/4 hydrogen and 1/4 helium by mass, distributed across an expanding space with no structure yet, no concentrations, no voids, just an almost perfectly uniform fog of primordial gas, stretching in every direction without boundary. Almost perfectly uniform. Not quite. There were tiny variations in density, regions fractionally denser than their surroundings, by amounts so small they would be invisible to any instrument that existed then. Those variations were the seeds of everything that followed. Gravity is patient. Over hundreds of millions of years, those fractional density differences grew. Slightly denser regions pulled surrounding material toward them. As they grew denser, they pulled harder. The surrounding gas, having nowhere else to go, fell inward. The uniform fog of primordial hydrogen and helium began to develop structure, filaments and sheets and knots of gas, condensing out of the background, the denser regions becoming what would eventually be recognized as the first nebulae. Not the colorful, glowing structures visible in telescope images today. Something darker and colder, vast clouds of primordial gas, contracting slowly under their own gravity, carrying nothing heavier than lithium, containing no carbon, no oxygen, no iron, no silicon. The raw ingredients of the universe at that point were almost entirely the two simplest elements that exist. Everything heavier than lithium that exists anywhere in the universe today was made later, inside stars, and returned to space through processes violent enough to scatter it across interstellar distances. The nebulae visible now are not made of primordial material alone. They are a mixture, primordial hydrogen and helium, supplemented by everything that generations of stars have since manufactured and expelled. Understanding how that supplementation happened requires understanding what stars do to the material they are born from and what they give back when they die. A gas cloud sitting in space has no obvious reason to do anything. It is not moving toward anything in particular. It is not reacting chemically. It is not radiating significant energy. Left to its own devices, it should simply persist, drifting slowly with whatever motion it inherited from the larger structures around it, stable and inert across timescales that dwarf anything in human experience. The intuitive expectation is equilibrium. Gas spreads out, pressure pushes outward. Things disperse rather than concentrate. A cloud in space should gradually thin and dissipate rather than collapse inward on itself. Gravity disagrees. Every particle of gas in the cloud exerts a gravitational pull on every other particle. The pull is weak for any individual pair, almost unmeasurably weak given how diffuse the cloud is. But it is present across the entire volume, acting simultaneously on every part of the cloud, and it always points inward. Gravity has no repulsive component. It does not push. It only ever pulls, and in a gas cloud it pulls every part of the cloud toward every other part simultaneously. The question is not whether gravity is pulling the cloud inward. It always is. The question is whether something is pushing back hard enough to prevent collapse. In a stable gas cloud, something is. The thermal pressure of the gas, the outward push produced by the random motion of particles bouncing against each other, counteracts the gravitational pull. The cloud sits in a balance between inward gravity and outward pressure, neither collapsing nor dispersing, stable as long as the balance holds. That balance has a precise condition attached to it, worked out by the British physicist James Jeans in the early 20th century. A cloud below a certain mass, or above a certain temperature, or less dense than a certain threshold, is stable against collapse. The thermal pressure wins. But a cloud massive enough, cold enough, or dense enough crosses a threshold beyond which gravity overwhelms the pressure and collapse becomes inevitable. Several things can push a cloud across that threshold. It can simply accumulate enough mass by sweeping up surrounding material. It can cool, reducing its thermal pressure until gravity takes over. Or it can be disturbed from outside, compressed by a shock wave from a nearby stellar explosion, tipped from marginal stability into irreversible collapse by a single violent event. Once collapse begins, it does not reverse. The cloud falls inward, and as it falls, it releases gravitational potential energy as heat, which raises the temperature and pressure, but never fast enough to arrest the collapse entirely. The interior grows hotter and denser, while the outer layers continue falling inward, and the cloud that was drifting passively through space becomes something new entirely. A collapsing gas cloud does not fall inward as a single unified object. It fragments. As different regions of the cloud collapse at slightly different rates, local density variations that were negligible when the cloud was stable become significant once collapse is underway. A region that is fractionally denser than its surroundings collapses faster, pulling material toward it more strongly, growing denser still. The collapse is not uniform, it is lumpy, and the lumpiness amplifies itself as it proceeds. What began as a single cloud becomes a collection of collapsing fragments, each one independently falling inward on its own center of gravity, each one destined to become its own object, rather than contributing to a single massive result. This fragmentation is why the sky contains hundreds of billions of stars, rather than a much smaller number of extraordinarily massive ones. A single cloud massive enough to collapse under its own gravity contains far more material than a single star needs. Left to collapse as one object, it would produce something so massive that its own radiation pressure would halt further star formation, and the remaining material would be blown away before it could ignite. Fragmentation prevents this. The cloud breaks into pieces during collapse, each piece collapsing independently, and the result is a cluster of stars born roughly simultaneously from the same parent cloud, siblings in both composition and age. Each fragment follows the same trajectory. As it collapses, the gravitational potential energy of infalling material converts to heat. The interior warms, the density rises, the fragment develops a structure, a denser, hotter core surrounded by infalling material still raining down from the outer regions of the fragment. At this stage, the object is called a protostar, not yet a star because nuclear fusion has not begun, but no longer simply a gas cloud because the collapse has already created a concentrated object with a definable center and a temperature far above anything in the surrounding interstellar medium. The protostar continues to grow as material falls onto it. Its core temperature climbs, its density rises toward values that have no terrestrial equivalent. The infalling material does not arrive quietly. It carries angular momentum, the same property that keeps a spinning skater spinning when she pulls her arms in, and as the material falls inward, that angular momentum concentrates. The protostar spins faster as it shrinks, and the material that cannot fall directly onto the core due to its rotation spreads into a disk around the protostar's equator, a flat rotating structure of gas and dust that will later become the birthplace of planets. The protostar sits at the center of this disk, still growing, still heating, approaching the threshold that separates a collapsing object from a star. The core of a protostar is a place of steadily increasing extremity, temperature climbing, density rising, the infalling material compressing everything beneath it with the full weight of the accumulating mass above. At the center of a protostar destined to become a sun-like star, the temperature is climbing toward 10 million degrees, and the density is approaching values where individual atoms no longer exist as distinct entities. The electrons have long since been stripped from their nuclei by the violence of the thermal environment. What remains is a plasma, bare atomic nuclei moving at speeds determined by the temperature, colliding constantly, bouncing off each other in encounters governed by the electromagnetic repulsion between their positive charges. Most of those collisions are elastic. Two protons approach. The electromagnetic repulsion between them slows them. They deflect away from each other and continue on different trajectories, carrying the same total energy they arrived with. Nothing is created and nothing is destroyed. At lower temperatures, this is essentially the only outcome. The protons never get close enough for anything else to happen. The electromagnetic barrier between them, the repulsion that grows stronger as they approach, is simply too large relative to their kinetic energy for them to bridge the gap. At 10 million degrees, the kinetic energies are different. The protons are moving fast enough that some fraction of collisions carry sufficient energy to bring the two nuclei within range of the strong nuclear force, the force that operates only at extraordinarily short distances, but that, within those distances, overwhelms electromagnetism completely. When two protons get close enough for the strong force to engage, fusion becomes possible. The two nuclei can stick together rather than bouncing apart, releasing energy in the process as the mass of the combined system turns out to be slightly less than the mass of the two separate protons. That missing mass has become energy in accordance with the relationship between mass and energy that sits at the foundation of nuclear physics. The moment sustained fusion begins at the core, the protostar crosses a threshold it will not recross for millions or billions of years. The energy released by fusion creates an outward pressure that pushes back against the inward pull of gravity. The collapse that has been proceeding since the fragment first separated from its parent cloud finally meets a force capable of opposing it. The protostar stabilizes. It is no longer collapsing. It is no longer simply a protostar. It is a star, and it will remain one for as long as its fuel holds out. A star is not burning in any chemical sense. Nothing is combusting. There is no oxygen feeding a flame, no fuel being oxidized the way wood burns in a fireplace or gasoline burns in an engine. The process happening at a stellar core is nuclear fusion, the joining of light atomic nuclei into heavier ones. And the energy it releases comes not from chemical bonds breaking and reforming, but from the conversion of a small fraction of nuclear mass directly into energy. The Sun converts roughly 4 million tons of its own mass into energy every second. It has been doing this for 4.5 billion years and will continue for approximately another 5 billion. The fuel supply is not trivial. What makes a star stable for those billions of years is a self-regulating feedback loop between gravity and radiation pressure that keeps the balance without any external management. If the core temperature rises slightly, fusion rates increase, more energy is released, the outward pressure increases, the core expands slightly, the temperature drops back down, and fusion rates return to their previous level. If the core cools slightly, the process runs in reverse. The star squeezes itself until the temperature recovers. The balance is not static, it is dynamic, continuously adjusting, correcting deviations before they can grow large enough to matter. A star on the main sequence is a self-stabilizing nuclear reactor operating under conditions no human engineering has come close to replicating. The surface of that reactor is what becomes visible as starlight. Energy generated at the core does not travel to the surface quickly. A photon produced by fusion at the Sun's center takes on average around 100,000 years to random walk its way outward through the dense solar interior, absorbed and re-emitted countless times before finally reaching the surface and escaping into space. The light arriving at Earth from the Sun left the solar surface 8 minutes ago, but was generated at the core long before human civilization existed. The star's surface, its photosphere, is where the interior energy finally escapes, and its temperature at that surface determines the color of the light it emits. Hotter stars burn blue-white, cooler ones burn orange and red. The Sun, a middle-temperature star, burns yellow-white. Around that burning core and luminous surface, the remnants of the nebula that formed it are still present, now shaped and transformed by the star's existence. What a star does to its birth, nebula is not passive. The moment fusion ignites, the surrounding gas begins to feel the consequences. A newborn star is not a quiet neighbor. From the moment fusion ignites, it begins reshaping everything around it with a thoroughness that eventually leaves nothing of the original cloud unchanged. The mechanisms are several, and they operate simultaneously, each one acting on the surrounding gas in a different way, collectively producing the structures that telescopes reveal when they image star-forming regions. The most immediate effect is radiation. A hot, young star, particularly one more massive than the Sun, pours ultraviolet photons into the surrounding gas at a rate that the gas cannot absorb without responding. Ultraviolet radiation carries enough energy to strip electrons from hydrogen atoms, ionizing them, converting neutral gas into plasma. The region of ionized gas surrounding a hot young star is called an H2 region, named for ionized hydrogen, and it glows in the characteristic pink-red of hydrogen recombination emission. The light produced when stripped electrons find their way back to protons and release the energy of that reunion as a photon. The Orion Nebula is an H2 region. So are most of the colourful, glowing nebulae in telescope images. Their glow is the direct consequence of a hot star's radiation tearing the surrounding gas apart and the gas continuously reassembling itself. Beyond the ionized zone, the radiation pressure itself pushes outward. Photons carry momentum, and when they are absorbed by dust grains in the surrounding cloud, they transfer that momentum to the dust. Enough photons hitting enough dust grains produces a net outward force, a radiation pressure that pushes the surrounding material away from the star. Combined with the stellar wind, a continuous outflow of charged particles from the star's surface moving at hundreds of kilometers per second, this outward pressure carves a cavity in the surrounding nebula. The star hollows out a bubble in its birth cloud, compressing the gas at the bubble's edge into a dense shell that glows at the boundary between the ionized interior and the neutral exterior. That compressed shell at the bubble's edge is not merely a byproduct of the star's existence, it is a trigger. The compression raises the density of the gas at the shell above the Jeans threshold, the same threshold that governs whether a gas cloud collapses under gravity. New collapse begins in the compressed shell. New protostars form at the edge of the bubble blown by the first star. A single massive star igniting in a gas cloud can trigger a cascade of star formation in the surrounding material, each new star compressing more gas, each compression potentially triggering further collapse. Star formation propagates through a molecular cloud the way a lit match moves through dry grass, each ignition creating the conditions for the next. The nebula that produced the star is being consumed and transformed simultaneously. Ionized, compressed, blown outward, triggered into new collapse. The cloud that was drifting passively through space is now a dynamic system driven by the energy of the objects it created, and it will continue in this state until the most massive of those objects reaches the end of its fuel supply. What happens then depends entirely on how massive the star is. A star like the Sun has roughly 10 billion years of hydrogen fuel in its core. For most of that time, it sits on the main sequence, stable, self-regulating, burning steadily through its supply with the patient consistency of a process operating on timescales that make geological time look brief. But the fuel is finite. As hydrogen in the core is consumed and converted to helium, the composition of the core gradually shifts. The hydrogen does not run out suddenly. It depletes slowly, and as it does, the core's ability to sustain the fusion rates needed to support the star against gravity begins to diminish. The core responds by contracting. With less fusion energy pushing outward, gravity wins a little more ground, squeezing the core tighter, raising its temperature and density. The higher temperature ignites hydrogen fusion in a shell surrounding the now helium-dominated core, a ring of burning hydrogen sitting just outside the inert helium center. This shell fusion produces more energy than the core fusion it replaces, and the excess energy pushes the outer layers of the star dramatically outward. The star expands. Its surface cools as it spreads across a larger area. Its color shifts from yellow-white toward orange and red. The star has become a red giant, its outer atmosphere now extending to distances that would engulf the inner planets of a solar system like ours. Inside the expanding outer layers, the helium core continues to contract and heat. Eventually, in a star of roughly solar mass, the core temperature reaches the threshold for helium fusion. Helium nuclei begin fusing into carbon and oxygen, a new energy source igniting in the core and stabilizing the star briefly in a new configuration. The red giant phase is not the end, it is a transition, the star restructuring itself around a new fuel source, while its outer layers drift ever further from the center. The helium fuel does not last as long as the hydrogen did. When it too is exhausted, the core contracts again, but a sun-like star does not have enough mass to generate the temperatures needed to ignite carbon fusion. The core stalls. It becomes a dense sphere of carbon and oxygen, supported not by fusion but by the quantum mechanical pressure of tightly packed electrons resisting further compression. The outer layers, no longer held by sufficient gravity against the radiation from the contracting core, drift away into space. They expand outward as a slow-moving shell of gas, illuminated by the hot remnant core at the center, glowing in the colors of their constituent atoms. This expanding shell is a planetary nebula, named by early astronomers who thought the round glowing structures resembled planets through their telescopes. They bear no relation to planets. They are the shared outer layers of a dying star, expanding into the surrounding interstellar medium, carrying with them the carbon and oxygen and nitrogen that the star spent billions of years manufacturing in its core. The shell of gas expanding away from a dying sun-like star is one of the most visually striking structures in the universe and one of the most consequential. From a distance it appears as a luminous ring or bubble, sometimes symmetric and geometric, sometimes asymmetric and irregular, depending on the rotation of the star that produced it and the distribution of material in the surrounding space. The hot white dwarf at its center, the collapsed remnant of the stellar core, pours ultraviolet radiation into the expanding shell, ionizing it, causing it to glow in the same hydrogen recombination emission that lights up H2 regions around young stars. The colors visible in telescope images are the emission lines of specific elements: hydrogen in red, oxygen in blue-green, nitrogen in red-orange, each one a signature of the nuclear history of the star that made them. That nuclear history is written into the composition of the shell. The carbon in it was not there when the star formed. It was manufactured inside the star over billions of years of helium fusion, built up atom by atom in the stellar core, and mixed into the outer layers during the red giant phase through convective processes that dredged core material upward into the envelope. The nitrogen was produced through a separate chain of nuclear reactions operating in the hydrogen-burning shell. The oxygen came from helium fusion alongside the carbon. Every atom heavier than helium in that expanding shell was forged inside the star from the simpler material the star was born with, and it is now being returned to the interstellar medium, available to be incorporated into the next generation of stars and planets, and whatever else gravity and chemistry eventually assemble from it. The white dwarf left behind at the center will cool over billions of years, its surface temperature dropping as it radiates away its remaining heat, with no new energy source to replace it. It will fade from white to yellow to orange to red, over timescales comparable to the current age of the universe, eventually becoming a cold, dark sphere of carbon and oxygen drifting invisibly through space. But the shell it ejected will long since have merged with the surrounding interstellar medium, its material dispersed into the vast reservoir of gas and dust from which future stars will form. The star is gone. Its contribution to the chemical inventory of the galaxy is permanent. A sun-like star processes the material it was born with, enriches it, and returns it. The cycle it participates in is real and measurable, visible in the compositions of stars of different ages, traceable across the history of the galaxy. But the contribution of sun-like stars to the chemical enrichment of the universe, while significant, is modest compared to what happens when a much more massive star reaches the end of its life. The deaths of massive stars are not gentle dispersals of outer layers. They are among the most energetic events the universe produces, and what they put back into space is categorically different from anything a planetary nebula can offer. A star 10 times the mass of the Sun does not have 10 times the lifespan. It has a fraction of it. The relationship between stellar mass and stellar lifetime runs in the opposite direction from intuition. More massive stars have more fuel, but they burn it at a vastly higher rate, because the greater gravity pressing down on their cores demands greater fusion rates to maintain the balance against collapse. A star 10 times the Sun's mass burns through its hydrogen in tens of millions of years, rather than billions. A star 50 times the Sun's mass may exhaust its core hydrogen in just a few million years, a blink in cosmic time, barely long enough for the galaxy to complete a fraction of a single rotation before the star is already dying. The death of a massive star follows the same opening sequence as a sun-like star. Hydrogen in the core depletes, the core contracts, a hydrogen-burning shell ignites around the helium core. The outer layers expand, and the star becomes a red supergiant, swelling to dimensions that dwarf anything a sun-like star achieves in its red giant phase. Betelgeuse, the bright reddish star marking Orion's shoulder, is a red supergiant. If placed at the center of our solar system, its surface would extend past the orbit of Jupiter. The star is so large that the light travel time from one side to the other takes hours. Inside that enormous envelope, the core is doing something a sun-like star's core never manages. The temperature and density are high enough to ignite carbon fusion after the helium is exhausted. Carbon fuses into neon and magnesium. When the carbon is gone, the core contracts again, heats again, and ignites neon fusion. Then oxygen fusion, then silicon fusion. Each fuel cycle is shorter than the last, because each successive fuel releases less energy per reaction, while the star's luminosity remains enormous, consuming the new fuel at a punishing rate. The final fuel cycle, Silicon fusing into iron lasts on the order of days. Iron is where the sequence terminates, and it terminates with a totality that has no parallel in the earlier fuel cycles. Every previous fusion reaction released energy because the product nucleus was more tightly bound than the reactants, and the difference in binding energy appeared as the energy that powered the star. Iron sits at the peak of the binding energy curve. Fusing iron does not release energy, it consumes it. The moment the core becomes iron, fusion stops being a source of energy and becomes a drain on it. The core has been supported against gravity by the energy of fusion for millions of years. That support vanishes in less than a second. What follows happens faster than any process in stellar physics. The iron core, now unsupported, collapses under its own gravity at a significant fraction of the speed of light. In a fraction of a second, it goes from a sphere roughly the size of Earth to a sphere roughly 20 kilometers across, a neutron star, compressed so tightly that protons and electrons are forced together into neutrons, and the density reaches that of an atomic nucleus across an object the size of a city. The infalling outer layers, still rushing inward when the core suddenly stops collapsing and becomes incompressible, slam into the neutron star surface and rebound outward in a shock wave of almost incomprehensible energy. The shock wave moving outward from the rebounding core carries more energy than the sun will radiate across its entire 10 billion year lifespan. It tears through the infalling stellar envelope, accelerating the outer layers of the star to velocities of tens of thousands of kilometers per second, and when it reaches the stellar surface, it produces a flash of light so intense that the exploding star briefly outshines the entire galaxy containing it. Every star in the galaxy, hundreds of billions of them, contributing their combined luminosity to a single point of light, and a single dying star matching that output for days or weeks. This is a supernova, and it is not primarily a light show. The light is a byproduct. The supernova is fundamentally a dispersal event, the most thorough and violent recycling mechanism the universe operates. Everything the star accumulated and processed over its millions of years of existence is now being ejected into the surrounding space at a significant fraction of the speed of light. The hydrogen and helium from the outer layers that never made it into the core, the carbon, neon, magnesium and oxygen from the successive fusion shells, the silicon and sulfur from the innermost shells, and something else, something that none of the fuel cycles inside the star could produce. The shockwave itself, as it tears through the stellar layers, creates conditions of temperature and density extreme enough to drive fusion reactions that the star's core never achieved. Elements heavier than iron, which cannot be built by normal stellar fusion because iron is the energy floor, are forged in the seconds of the explosion itself, neutrons slamming into existing nuclei faster than those nuclei can decay, building up through the periodic table to produce copper, zinc, gold, platinum, uranium, and every other heavy element that exists in the universe. Gold does not form in stellar cores. It forms in the last seconds of a massive star's life, or in the collision of two neutron stars, events violent enough to drive nuclear synthesis past the iron barrier that normal fusion cannot cross. Every gold atom that has ever existed was produced in a cataclysm. The ring on a finger, the contacts in a circuit board, the reserves in a vault. All of it was forged in stellar violence and scattered across interstellar space before the solar system existed. The material ejected in a supernova does not disperse uniformly into the surrounding space. It expands outward as a shell, the supernova remnant, a structure of shocked and heated gas carrying the full chemical inventory of the dead star, moving through the interstellar medium at velocities that compress and heat whatever it encounters. The remnant is not simply debris, it is an active agent in the galaxy's chemistry and star formation history, and its effects on the surrounding interstellar medium propagate far beyond the volume it directly occupies. The shell of material expanding outward from a supernova carries a chemical complexity that the universe did not possess before stars existed. Hydrogen and helium were there from the beginning, products of the Big Bang nuclear synthesis that occurred in the first few minutes of cosmic history. Everything else, every element heavier than lithium in the periodic table, was made inside stars and returned to space through stellar death. The supernova remnant is a moving library of nuclear history, its composition a record of every fusion process that operated inside the star that produced it, and every rapid neutron capture reaction that occurred during the explosion itself. That composition is not uniform across the remnant. The star that exploded had a layered internal structure, each layer reflecting a different fuel cycle, operating at a different temperature and density. The outermost layers were hydrogen and helium, barely processed from their original composition. Beneath them were the products of hydrogen shell burning, nitrogen and carbon mixed into the envelope during the red giant phase. Deeper still were the carbon and oxygen layers from helium burning, then the neon and magnesium from carbon burning, then the oxygen and silicon from neon and oxygen burning, then the iron core at the center, now a neutron star rather than part of the ejector. As the supernova blast tears through these layers, it mixes them, but not completely. The remnant carries a chemical gradient, a memory of the star's internal architecture preserved imperfectly in the distribution of elements across the expanding shell. The remnant expands and cools over thousands of years. The fastest moving material at the outer edge of the shell has already swept up and compressed a significant volume of surrounding interstellar gas, creating a dense shell of shocked material that glows in X-rays and radio waves as well as visible light. The Crab Nebula, the remnant of a supernova observed by Chinese astronomers in 1054, is still expanding today. Its filaments of ejected stellar material visible in telescope images as a tangled web of glowing gas surrounding the pulsar, a rapidly rotating neutron star at its center. Cassiopeia A, a younger remnant, shows the layered chemical structure of its parent star preserved in the spatial distribution of different elements across the expanding shell, readable by X-ray telescopes, sensitive to the emission lines of specific atoms. Embedded in all of this chemistry is the raw material for everything that will form in the region of the galaxy that the remnant is moving through. The carbon that will eventually find its way into organic molecules, the oxygen that will bond with hydrogen to make water, the silicon that will aggregate into rocky planet interiors, the iron that will form planetary cores and flow as hemoglobin through the blood of whatever biology eventually assembles itself from these ingredients. None of it existed in this form before the star lived and died. All of it is now moving outward through the interstellar medium at velocities that will carry it across hundreds of light years before it finally slows and mixes into the surrounding gas. The expanding shell of a supernova remnant does not move through empty space. The interstellar medium it travels through is not a vacuum. It is a diffuse mixture of gas and dust, unevenly distributed, with regions of higher and lower density threading through each other across the galaxy. When the supernova shockwave encounters a denser region, a cloud of gas that has been sitting in marginal stability, the collision compresses the cloud from one side, raising its density above the gene's threshold, tipping it from stable equilibrium into gravitational collapse. The shockwave that destroyed one star triggers the birth of others. This is not a rare or incidental process. It is one of the primary mechanisms by which star formation propagates through a galaxy. A massive star forms, lives briefly by stellar standards, explodes, and the shock wave from its death compresses surrounding gas clouds into collapse. Those clouds produce new stars, some of which are massive enough to live briefly, and die violently in their own supernovae, producing new shock waves that compress new clouds. The process is not a simple chain reaction. It is a spatially extended, temporally overlapping cascade of events in which the death of each generation of massive stars seeds the birth of the next, and the galaxy's star formation history is written in the pattern of these cascades, spreading across its disk over billions of years. The material deposited by the supernova remnant mixes into the clouds it compresses. The next generation of stars that forms from those clouds is not forming from the same material the previous generation formed from. It is forming from a mixture of primordial gas and the processed enriched ejecta of every previous stellar generation that has contributed material to that region of the galaxy. Each successive generation of stars is born with a higher abundance of heavy elements than the one before it. The oldest stars in the galaxy, formed from nearly primordial material in the galaxy's earliest history, contain almost no elements heavier than helium. Stars formed more recently, like the Sun, contain a few percent by mass of heavier elements, a reflection of the cumulative contributions of billions of previous stellar generations to the galactic chemical inventory. The Sun is a third or fourth generation star. The material it formed from had already passed through multiple cycles of stellar birth, processing, and violent dispersal before gravity assembled it into the solar nebula 4.6 billion years ago. The heavy element abundance of the Sun and of the planets that formed from the leftover material of the solar nebula is a direct measure of how many previous stellar generations lived and died in this region of the galaxy before the Sun ignited. The iron in Earth's core, the silicon in its mantle, the carbon in every living thing on its surface, all of it carries the history of those previous generations encoded in its very existence. The universe at the moment of the Big Bang was chemically almost empty. Hydrogen and helium, trace lithium, nothing else. A universe containing only those three elements is a universe without water, without rock, without carbon chemistry, without any of the molecular complexity that biology requires. It is a universe that can form stars and black holes and neutron stars, but not planets with solid surfaces, not oceans, not atmospheres with a chemical richness that makes them interesting. The periodic table as it exists today, with 92 naturally occurring elements ranging from hydrogen to uranium, is not a feature of the universe as it was born. It is something the universe built for itself over billions of years through the mechanism of stellar nucleosynthesis and violent dispersal. The building happened in stages, each one adding to the chemical inventory available for the next. The first generation of stars, called Population 3 stars by astronomers, formed from nearly pure hydrogen and helium in the early universe. They were likely massive, burning through their fuel quickly, dying in supernovae that seeded the surrounding intergalactic medium with the first heavy elements ever to exist anywhere. Carbon, oxygen, neon, magnesium, silicon, iron, and the full suite of heavy elements forged in their explosions dispersed into gas that had never contained anything heavier than lithium. The universe's chemical vocabulary expanded from 3 words to dozens in the deaths of that first stellar generation. The second generation of stars formed from gas, already enriched by those first supernovae. They were born with small but non-zero abundances of heavy elements, enough to change their internal physics slightly, enough to allow the formation of dust grains in their outflows, enough to begin the slow accumulation of solid material that would eventually make rocky planets possible. Their deaths enriched the interstellar medium further, adding their own nucleosynthetic contributions to the growing chemical library. Each subsequent generation inherited a richer starting composition and returned a richer mixture to the interstellar medium when it died. This progressive enrichment is measurable. Astronomers can determine the heavy element abundance of a star from its spectrum, the pattern of absorption lines that specific elements imprint on starlight passing through the stellar atmosphere. Old stars formed early in galactic history show low, heavy element abundances. Young stars formed recently from gas that has been through many cycles of stellar processing show higher abundances. The Sun sits at an intermediate position on this scale, its heavy element content reflecting 4.6 billion years of galactic chemical evolution preceding its formation. The trend across stellar populations is not subtle. It is one of the clearest signatures in observational astronomy of the cumulative effect of billions of years of stellar birth, processing and death operating continuously across the galaxy. Not all nebulae glow. The colourful emission nebulae visible in telescope images, the HII regions lit up by hot young stars, are the most visually prominent structures in the interstellar medium, but they are not the most important ones for star formation. The most fertile regions of the galaxy are darker and colder, invisible to optical telescopes, detectable only through radio and infrared observations that can penetrate the dense dust that makes them opaque to visible light. These are molecular clouds, and they are where the overwhelming majority of star formation in the galaxy occurs. A molecular cloud is a region of the interstellar medium dense enough and cold enough that hydrogen exists not as individual atoms but as molecules, two hydrogen atoms bound together into H2. The transition from atomic to molecular hydrogen requires conditions that are not met in the diffuse interstellar medium. The gas must be dense enough that hydrogen atoms collide frequently enough to form molecules, and cold enough that the molecules are not immediately dissociated by ultraviolet radiation. Dust plays a critical role here. The dust grains that thread through molecular clouds absorb ultraviolet photons before they can penetrate deep into the cloud, shielding the interior from the radiation that would otherwise prevent molecule formation. The dust that seems like an obstacle to observation is actually a prerequisite for the chemistry that makes molecular clouds the nurseries they are. Inside a molecular cloud, the chemical complexity goes far beyond molecular hydrogen. Radio astronomers have detected over 200 distinct molecular species in molecular clouds, ranging from simple diatomic molecules like carbon monoxide, which is the second most abundant molecule after hydrogen, and the primary tracer used to map molecular clouds across the galaxy, to increasingly complex organic molecules. Formaldehyde, methanol, ethanol, glycine, and amino acid has been detected in the interstellar medium. The chemistry happening in the cold, dense interior of a molecular cloud, driven by reactions on the surfaces of dust grains at temperatures only a few degrees above absolute zero, is not simple. It is the beginning of the organic chemistry that life eventually uses, occurring in the nebula long before any planet forms to host it. Molecular clouds are also the largest discrete structures in the galaxy. Giant molecular clouds can contain millions of times the mass of the Sun spread across hundreds of light years, harboring within them the material for thousands of stellar systems simultaneously. The Orion molecular cloud, the larger structure of which the visible Orion Nebula is merely the illuminated face, contains enough material to form tens of thousands of stars. It is actively doing so. The star formation happening in the Orion Nebula is one small region of activity within a much larger cloud that is collapsing and fragmenting across its entire volume, producing stellar clusters and associations that will eventually disperse into the galaxy's disk as their parent cloud is consumed. A protostar does not consume all the material that falls toward it during collapse. The angular momentum of the infalling gas, the same rotational property that makes a spinning top resist falling over, prevents a significant fraction of the cloud fragment's mass from reaching the protostar directly. Material with too much angular momentum to fall straight inward settles into a rotating disk around the protostar's equator, a flattened structure of gas and dust that can contain anywhere from a fraction of a percent to several times the mass of the central star, depending on the specific conditions of the collapse. This disk is called a protoplanetary disk, and it is where planets come from. The disk is not a uniform sheet of material. It has structure, temperature gradients running from hot near the protostar to cold at the outer edges, density variations, and a composition that reflects the temperature at each distance from the center. Close to the protostar, where temperatures are high enough to vaporize most solids, only refractory materials, minerals with very high melting points, can exist as solid grains. Further out, beyond what astronomers call the snowline, temperatures drop below the condensation point of water ice, and the solid material available for planet building increases dramatically as ice joins the refractory grains. The snowline is not a minor detail. It is the boundary that separates the rocky inner solar system from the gas and ice giant outer solar system in our own planetary system, and it plays the same role in every protoplanetary disk around every forming star. Planet formation begins with dust grains colliding and sticking together. Two grains colliding at low velocity can adhere through electrostatic forces and van der Waals interactions, the same quantum vacuum-mediated attraction that operates between neutral atoms. Stuck together, the combined grain presents a larger surface area for further collisions. It grows. The growth from a microscopic dust grains to centimeter-sized pebbles happens relatively quickly by astronomical standards. But the next stage is harder. Centimeter to meter-sized objects collide at velocities high enough to fragment rather than stick, a size range where neither the gentle adhesion that works for dust grains nor the gravitational attraction that operates between larger bodies is sufficient to ensure growth rather than destruction. This meter-size barrier is one of the outstanding problems in planet formation theory, and several mechanisms have been proposed to cross it. Streaming instability, a process where aerodynamic interactions between gas and solids cause pebbles to concentrate into dense filaments that collapse gravitationally into larger bodies, appears to be the most promising. Once objects reach kilometer scale, called planetesimals, gravity takes over and growth becomes self-sustaining. Larger planetesimals attract smaller ones gravitationally, sweeping up material across their orbital neighborhood, growing into protoplanets and eventually into the planets that orbit the finished star. The entire process from dust grain to planet takes millions of years, brief compared to the lifespan of the star, but long enough that the protoplanetary disk has largely dispersed by the time the planetary system reaches its final configuration. Every atom in every planet that has ever formed around any star in the history of the universe was once part of a nebula, not metaphorically, not approximately. The hydrogen in Earth's oceans was primordial, present in the solar nebula from the beginning, inherited directly from the molecular cloud that collapsed to form the solar system. The oxygen bonded to that hydrogen was forged in the helium-burning shells of stars that died before the sun existed, returned to the interstellar medium through planetary nebulae and supernova explosions, mixed into the molecular cloud over hundreds of millions of years, and eventually incorporated into the rotating disk of gas and dust from which Earth assembled itself. The iron in Earth's core travelled the same route, manufactured in the silicon-burning shells of massive stars, ejected in supernovae, dispersed across interstellar distances, concentrated by gravity into the solar nebula, and finally drawn by that same gravity into the growing protoplanet that became this world. The same accounting applies to every atom in every living thing. The carbon in every organic molecule that has ever existed on Earth was forged in a stellar core. The nitrogen in every protein, every DNA base, every cell membrane was produced in hydrogen-burning shells of stars that never knew this planet would exist. The phosphorus in the backbone of every DNA molecule in every organism that has ever lived was synthesized in a supernova. The calcium in bone, the potassium in nerve cells, the sulfur in proteins, the zinc in enzymes, every element that biology uses for every purpose, it uses them for, arrived on this planet as part of the chemical inheritance left by previous stellar generations, delivered through the nebula that the Sun and solar system formed from. This is not a poetic observation about cosmic connectedness. It is a precise statement about chemistry and nuclear physics and the history of matter. The atoms currently assembled into a human body have each travelled an extraordinary path. Forged in stellar interiors or violent explosions, dispersed across interstellar space, incorporated into a molecular cloud, swept into a protoplanetary disk, aggregated into a planet, cycled through geology and oceans and atmosphere and biology across billions of years, and currently organized into the specific configuration that constitutes a living organism. The organization is temporary. The atoms are not. When the organism dies, they will disperse again, back into the environment, available for whatever chemistry or geology or biology claims them next. On longer timescales, the planet itself is temporary. When the sun exhausts its hydrogen fuel and expands into a red giant, it will engulf the inner planets, vaporizing their surfaces and eventually dispersing their material back into the interstellar medium. The atoms that spent billions of years as part of Earth will become part of the planetary nebula that the sun's death produces, mixed back into the interstellar medium, available once again to be incorporated into the next generation of stars and planetary systems. The cycle does not have a natural endpoint visible from where we currently sit in cosmic time. Step back from the individual mechanisms and look at what they collectively describe. A universe that began with 3 elements and no solid matter has over 13 billion years built itself into a place containing 92 naturally occurring elements, hundreds of billions of galaxies, each containing hundreds of billions of stars, and at least one planet known to harbour organisms complex enough to look back at the process and ask how it works. The mechanism responsible for all of that elaboration is the cycle that nebulae sit at the centre of. Gravity assembles gas into stars. Stars process simple elements into complex ones. Stellar death returns the processed material to space. Gravity reassembles the enriched material into new stars and planets. Each cycle leaves the universe more chemically complex than it was before. This is not a cycle that was designed to produce complexity. It is a cycle that produces complexity as an unavoidable consequence of the physics involved. Gravity pulls things together. Nuclear physics releases energy when light nuclei fuse into heavier ones up to iron. The energy release supports the star against collapse long enough to process significant quantities of material. The same gravity that assembled the star eventually contributes to its death, either by providing the inward pressure that a sun-like star's outer layers eventually escape as a planetary nebula, or by driving the catastrophic core collapse that produces a supernova in a massive star. Death disperses what life manufactured. The dispersed material is available for the next cycle. The chemistry of each cycle is richer than the last, because each cycle inherits the products of all previous ones. There is no external agent managing this process. No mechanism ensures that the right elements are produced in the right quantities. No guidance system directs supernova shock waves toward gas clouds that need triggering. The entire elaboration of the universe, from primordial simplicity to chemical complexity, is an emergent consequence of a small number of physical laws operating without supervision across enormous scales of space and time. Gravity and nuclear physics and thermodynamics interacting across 13 billion years and hundreds of billions of galaxies have produced a universe that contains the periodic table, solid planets, liquid water, and carbon chemistry without any of those outcomes being specified in advance. What the nebula reveals in this picture is its own centrality. It is not merely the backdrop against which star formation occurs. It is the medium through which the cycle operates, the reservoir that receives the products of stellar death and holds them until gravity is ready to reassemble them into something new. The nebula is where the universe stores its work in progress, the accumulated chemical output of every previous stellar generation, mixed and preserved in interstellar space, waiting for the next gravitational instability to trigger the next round of assembly. Without nebulae, there is no mechanism for the processed material of dead stars to become the raw material of new ones. The cycle breaks. The chemical elaboration stops. The universe remains at whatever level of complexity it has reached and goes no further. There is a question sitting underneath everything described so far that has not been asked directly. Why does the universe do this? Not in a teleological sense, not asking what purpose the cycle serves, but in a more immediate physical sense. What is it about the laws of physics as they happen to be that produces a universe capable of building increasing chemical complexity across cosmic time, rather than remaining forever at the level of hydrogen and helium? The answer has several parts, and they fit together in a way that is not obvious until you see them simultaneously. The first is that gravity is attractive and has no repulsive component. This seems trivially true, but its consequences are not trivial. A universe with a repulsive gravitational force at short range would not form stars. The gas clouds that become stellar nurseries would be stabilized against collapse by the repulsion, and the cycle would never begin. Gravity's unrelenting inward pull is the engine that starts everything. The second is that nuclear fusion releases energy for elements up to iron, and consumes it for elements beyond iron. This asymmetry is not obvious from first principles. It is a consequence of how the strong nuclear force and electromagnetic repulsion balance against each other as nuclei grow larger, producing the binding energy curve with its peak at iron. A universe where fusion released energy for all elements regardless of mass would produce stars that burned through their fuel without ever producing the iron cores that trigger supernova collapse. A universe where fusion consumed energy for all elements would produce no stellar energy source at all. The specific shape of the binding energy curve, with iron at its peak, is what produces stars that live long enough to process significant quantities of material and then die violently enough to disperse it. The third is that the universe began with density variations, small enough that structure formation was gradual rather than immediate. If the primordial density variations had been much larger, the universe would have collapsed into black holes before stars could form. If they had been much smaller, the universe might have remained too uniform for gravitational collapse to ever produce stars on timescales shorter than the current age of the universe. The specific amplitude of the primordial density fluctuations sits in the range that allows gradual hierarchical structure formation, gas clouds collapsing into stars, stars assembling into galaxies, galaxies clustering into large-scale structure, each level of organization emerging from the previous one over cosmic time. None of these conditions were chosen. They are features of the universe as it happens to be, and together they produce a cosmos that is self-elaborating, that takes a simple starting condition and generates increasing complexity through the repeated operation of a small number of physical processes. The nebula is where that elaboration is most directly visible, the place where the products of the past and the raw material of the future exist simultaneously in the same cloud of gas and dust, waiting for gravity to begin the next cycle. Return to the smudge below Orion's belt. It looks the same as it did at the beginning, a faint, blurred point of light that resolves in a telescope into a glowing cloud of gas, pink and blue and threaded with darker lanes of dust, young stars burning at its center, the whole structure luminous against the black of surrounding space. Nothing about its appearance has changed. What has changed is what it is possible to see when you look at it. The gas in that cloud is not simply gas. It is the accumulated output of stellar generations that lived and died in this region of the galaxy before the sun existed. The hydrogen in it is primordial, 13 billion years old, present since the universe was minutes old. The carbon and oxygen mixed into it were forged in stellar cores and returned to space through planetary nebulae. The iron and silicon and sulfur were ejected in supernovae, some of them close enough to have contributed shock waves that compressed earlier versions of this same cloud into collapse, producing stars whose deaths enrich the material that the current cloud is made of. The Orion Nebula is not a static object. It is a moment in a process, a snapshot of material that has been cycling through stellar birth and death for billions of years, and will continue doing so long after the stars currently forming inside it have lived out their own lifespans. The protostars forming inside it right now will eventually ignite, clearing the surrounding gas with their radiation and stellar winds, producing HII regions that glow the same pink-red as the current nebula. Some of the more massive ones will live briefly and die in supernovae, their shock waves propagating outward into the molecular cloud surrounding the visible nebula, triggering new collapse in gas that has not yet begun to form stars. The less massive ones will shed planetary nebulae when they die, returning their processed material to the interstellar medium, giving whatever chemistry or biology eventually operates on their surfaces access to the full periodic table rather than just hydrogen and helium. The cycle visible in the Orion Nebula is the same cycle operating in every star-forming region in every galaxy across the observable universe. Billions of galaxies, each containing hundreds of billions of stars in various stages of the same process, collectively driving the chemical elaboration of the universe forward with every stellar generation. The universe is not winding down toward equilibrium. It is building, using the energy released by nuclear fusion to drive a cycle of assembly and dispersal that leaves the cosmos more complex after each iteration than it was before. The nebula is where that building happens, where gravity and chemistry and nuclear physics converge in a cloud of gas and dust and produce, with no supervision, and no blueprint, the raw material of everything that exists. The life cycle of a nebula is not a metaphor. It is not a narrative imposed on physical processes to make them easier to communicate. It is a description of something the universe actually does, a real cycle of assembly and dispersal operating across real time scales, producing real chemical complexity that accumulates with each iteration. The word cycle implies repetition, and the repetition is real, but it is not a closed loop returning to the same starting point. Each iteration begins from a chemically richer starting condition than the one before it. The universe does not repeat itself. It elaborates itself, using the same mechanisms in each cycle, but operating on progressively more complex material, producing progressively more complex outcomes. What a nebula reveals about the life cycle of the universe is that the universe has a direction, not a purpose, not a destination it is moving toward by design, but a direction in the sense that its chemical complexity increases monotonically with time. The second law of thermodynamics says that disorder increases in closed systems, and the universe as a whole is moving toward higher entropy. But within that overall trend toward disorder, gravity creates local pockets of order, assembling diffuse gas into stars and planets and everything that forms on planets. And nuclear physics uses those pockets of order to manufacture chemical complexity that persists after the order dissolves. The heavy elements forged in a stellar core do not disappear when the star dies. They disperse, but they remain as heavy elements, available to be incorporated into the next generation of stars and planets, and whatever else gravity assembles from them. The nebula sits at the boundary between these two tendencies. It is the place where dispersed material, entropy increased, order dissolved, waits to be reassembled. It is simultaneously the product of stellar death and the raw material of stellar birth, the end of one cycle and the beginning of the next, the universe exhaling and inhaling in a rhythm measured in millions of years. Every atom in the nebula has a history stretching back through multiple stellar lifetimes to the primordial gas of the Big Bang, and every atom in the nebula has a future that extends forward through stellar generations, not yet born to outcomes not yet imaginable. The smudge below Orion's belt is all of this at once, a cloud of gas doing what gas clouds do under gravity, a factory producing stars that will live and die and return their material to space, a library of nuclear history written in the abundances of elements that previous stars manufactured and scattered, a snapshot of a process 13 billion years old that will continue for billions more. It is not remarkable because it is exotic or distant or difficult to understand. It is remarkable because it is ordinary. Every gas cloud in every galaxy is doing the same thing. The universe is full of nebulae, and every one of them is the universe in the act of building itself from what it has already become.